This is your video set notes on metallic bonds and intermolecular forces. So metallic bonds we also call a sea of electrons, and that's because the electrons in a metallic bond are very mobile because the p orbital is empty, and in most cases the d orbital is not full. So we try to represent this movement by showing this diagram where those electrons are moving. Remember, metallic properties are that they have a high electrical conductivity, they're shiny, they're malleable, which means they can be flattened, and they're ductile, which means that they can make a wire. Metallic bond strength can also be measured by the heat of vaporization of the metal. Intermolecular forces is our next section here, and these are forces between molecules. So it's important to remember the difference between intermolecular forces and intramolecular forces. Intermolecular forces are between molecules. Intramolecular forces are within a molecule. So within a molecule we've got covalent, ionic, or metallic bonds. So now we're talking about between two different molecules. These intermolecular forces vary in strength but are usually weaker than ionic, covalent, and metallic bonding. Dipole forces are the first type of intermolecular force, and this is just saying that the dipole forces are a molecular attraction that exists between molecules having different polarity. So for example, if I've got HCl molecules here, the electronegativity difference of hydrogen and chlorine causes those electrons to hang out around the chlorine atom much more, which gives it a slightly negative charge. So that chlorine atom is going to be attracted to a hydrogen atom on a different HCl molecule, and we call that a dipole-dipole intermolecular force, or a dipole force. So the positive end, again, of a molecule is attracted to the negative end of a different molecule. Here's a diagram showing dipole forces where you can see that those molecules have a positive and negative end, and the relative size difference is showing where the electrons are hanging out, and it's just showing that attraction between those positive and negative ends. So that's essentially a dipole force, and it can happen on a lot of molecules, especially if there's a large electronegativity difference between atoms present in the molecule. Our next type of intermolecular force is a hydrogen bond. So hydrogen bonding is a particularly strong type of dipole-dipole force between molecules. The positive charge on a hydrogen end of one molecule is attracted to the unshared pair of electrons on another molecule. The hydrogen must be attracted to a nitrogen, oxygen, or fluorine, so I like to shorten that and say NOF, on another molecule. We represent hydrogen bonds with dotted lines. Basically, a hydrogen bond is why ice, or solid water, is less dense than liquid water, because as those hydrogen bonds form, the water molecules arrange in such a way that they trap air inside of it. So for example, here's a drawing of a hydrogen bond and how those water molecules arrange themselves so that they trap air in the middle of it. And again, that dotted line represents a hydrogen bond. Again, it's important to note that a hydrogen bond can be depicted or be represented both between a water molecule, but it also can be between a nitrogen, oxygen, or fluorine on another molecule. So HF molecule would also have a hydrogen bond present because that hydrogen is attracted to the unpaired electron pair on the outside of that fluorine molecule. So again, it does not necessarily always have to be with water that hydrogen bond is happening. London dispersion force is our last type of intermolecular force, and it's the intermolecular attraction that results from the uneven movement of electrons within a molecule. Even noble gases and nonpolar molecules have these moments of polarity because you never know where electrons are going to be at any given moment. So sometimes they can be on one side of an atom and for just a moment, and this sets up what we call moments of attraction to other molecules, or moments of polarity. So basically the Heisenberg theory is why we have London dispersion forces, because we've got electrons traveling around those atoms at different rates and we don't exactly know where they are at any given time. And here's an example of London dispersion forces where we've got that electron cloud and those electrons are moving variably around that nucleus. And so if we've got that electron cloud moving variably around the nucleus, we can show that there's an uneven distribution and it creates what we call an instantaneous dipole. So there's some positive and negative charges happening here, and it's creating an instantaneous dipole. And if we've got multiple molecules present, we can create moments of polarity and moments of attraction. So these are very weak intermolecular forces, but we do need to know that they still exist. Even larger molecules have London dispersion forces acting on them. So for example, if we've got this large molecule here, it actually would have quite a lot of London dispersion forces acting on it because there's way more electrons present to be able to move around the nuclei of those bonded atoms. And so it happens to nonpolar molecules. There's no unpaired electrons there, but there's still moments of polarity because of London dispersion forces. Alright, that's your video set notes on intermolecular forces and metallic bonds. Thank you for taking those notes and coming ready to class to review.